Good morning, good afternoon. Hello, everybody. Welcome to the first presentation of DBA Fundamentals for 2021. Today we have with us Argenis Fernandez from Pure Storage, doing a presentation on Storage 101 for DBAs. As you see here at the top right of our screen, we have three leaders of the group: Steve Cantrell, Shane O'Neill, and myself, Kevin Wilkie. You can reach us at the listed Twitter accounts. But then on the right, you'll actually see further down, you'll see the many ways you can get hold of us in various social media and other different ways. You can now reach out with us on the latest forum on Meetup on the DBA Fundamentals group. You can reach out to us on our website, through our YouTube channel, through Twitter, Slack, or LinkedIn. Now, as many of you have probably seen, PASS is going away. So we are going to actually be moving away from PASS. So our YouTube channel itself that is listed there will change. So please pay attention to us on Meetup. It's where one of the places you will be able to see a lot of things happening over the next several weeks. You can always find the latest there, as well as on our website. You'll see lots of things changing, but so many things will be staying the same. For example, all the people on this list for our leaders will be staying the same. And we hope to have all of our stuff, the different ways to reach us here will be staying, except for YouTube, which we'll show and share with you many things as we go forward. With that, we want to go to our next slide, which is one of our wonderful sponsors. There we go. All right. So our first one is DB Watch, which does a great complete solution for database administration, monitoring, performance tuning, security, and license management. If you have not gone to the website or checked out one of their trials, it is well worth the time. It is, they're one of the big things they do. The DB Watch Database Control Enterprise Manager truly is a great tool for if you have to work between, let's say, SQL Server, Oracle, many other different groups, then it's a great tool. Then our next sponsor is SentryOne, which has a multitude of different solutions and trials, things to look at, and different applications. So if you have not checked out any of their solutions before, especially Plan Explorer, it is well worth your time to do so. The Plan Explorer itself, it's free tool now. It's well worth every dime you pay for it and then some, because it does make exploring plans much easier and gives you lots of great help along the way as well. If you have any questions, please go on to their blog or website, especially the answers.sqlperformance.com, where there are lots of great tuning advice and great resources as well. Check them on their many different social media sites as well. As always, our sessions will be recorded and they will be out on this website within a couple of days. As I said earlier, as we transition to our new form, not under PASS, we will keep you up to date through many of our social media. So please be sure of that, and you can always check us out on our archives. And with that, we go to Argenis Fernandez, and I have listed here his bio, but I know most of you know and love Argenis, so you probably know most of this already. And so with that, Argenis, coming over to you.
All right, well, thanks for having me today, Kevin, Shane, Steve. It's a pleasure for me to present for you guys. I think it's been a while. I don't even remember when was the last time I presented for the DBA fundamentals group, VC. It's been at least several years, which, that's entirely my fault. Should have done this way earlier. But here we are. So the topic today is storage 101 for DBAs. I don't want to just focus on storage from the entire stack, from the application that SQL Server is all the way down to the storage devices. I really want to do a comprehensive, including devices kind of presentation, so we get an idea of, what it is all about. So when we hear all these things, we can connect the dots, and this is hopefully going to be an interesting one for you out there, because one of the most fundamental things about performance for databases is storage. If your storage is not up to snuff, your databases are going to perform badly. That's just how it is, right? And so the idea here is that we go over a comprehensive set of concepts that gets us a good understanding of how storage works with SQL Server throughout the entire stack, and we can connect the dots there when we have conversations at the higher level about storage. So why don't we go get started, and we talk a little bit about me, but this is going to be short because we don't really have a lot of time here. First of all, that bio that you guys had was a little bit outdated because I'm actually an MVP these days. Again, Microsoft did award the MVP award to me again, and I'm very thankful for that. And I'm also a current VMware vExpert because VMware also rewarded me the vExpert award last year. And so I've been doing a lot of things for SQL Server, including working for the SQL Server engineering team. It's been 23 years of working with the product. 23 or 24 at this point. I can't count. I don't know exactly what the number is. And I've been doing a lot of different things. I've been a DBA. That was the longest stretch of my career. I would say something like 15 years or longer as a DBA exclusively. So I've been doing a lot of different things for SQL Server, but my focus right now is storage, working for Pure Storage, who is a storage vendor. So storage devices, we'll definitely see some of the products that Pure Storage sells, because I won't mention just Pure Storage, by the way. I don't intend to make this a vendor presentation by any stretch, but I will highlight some of the things that my employer sells, and along with the others in the market that are well renowned, and some of the other technologies that Pure Storage doesn't even play on. Anyway, the agenda today, the basics of storage subsystems. We're gonna have to pick up the pace here because there's a lot to talk about. Basics alone is gonna take us a little bit of time to understand. We're gonna talk about the basics of SQL Server IO. We're gonna talk about database files, transactional log files, and file systems. We're going to talk about hypervisors, which is very important, right? Right now, most of you guys are running databases on top of hypervisors, and this is not just me talking. This is the hard data, right? If you're running on Azure or running on AWS or running on GCP, Google, or Oracle, you are running on top of a hypervisor no matter what, right? Only Amazon sells bare metal boxes, and I don't think anyone is running SQL Server on top of those because they're way too expensive and they have way too many CPUs, and they will have to pay for a lot of licensing. Anyway, protocols. Those are storage protocols, right, for communications between your hosts and your storage devices. And then the devices themselves, right? Because there's a myriad of them. There's literally a long list of devices. So I kind of categorize them into several devices, and we'll talk about them shortly. And then we'll talk about block and file system replication versus logical replication, because that's actually important, right? A lot of times we delegate HA and DR to the storage layer because it's easier. That's typically what's heard out there. I don't know that it's easier, but there's definitely arguments on either side of that discussion for performing replication on different sides of the different layers of the cake, so to speak. Anyway, let's get started, you guys. So basics of storage subsystems. Number one is latency. And this is one of the most important concepts because we need to understand what latency really means. Latency is the observed time that it takes to complete an IO at different places of the storage stack. And that's important, right? The storage stack includes your application. So latency simplified can be construed as simply how long does it take for an IO to complete, right? SQL Server says, I need to write something, and how long it actually takes for that IO to complete, meaning I issue a write against my storage device, right? I provide a buffer of memory that contains some data, and I want to write it to some storage device. You know, that storage device is going to take some time to write it down. I'm going to have to pass that IO down several layers. If I have a hypervisor, I'm going to be passing it through the hypervisor. And finally, it's going to make it to the device. And the device is going to reply and say, yep, I completed that IO. And the measurement of the elapsed time between issuing that IO and receiving confirmation that that IO completed, that's your latency right there, simply put. And obviously, when you're performing reads, you're not sending a buffer of memory down, but you're saying, oh, I want this particular offset within this particular volume or LUN within this particular storage device. Can I please get that? And so that read would also take some time to complete, and then the latency for that read will be also taken into consideration for performance metrics. So that simply put is how long did my IO take to complete? The second and very important concept here for a storage subsystem is the IO block size, also known as the request size. This is super important because not all IO is the same, right? If you're talking about transactional log IO, for example, you're talking about small block IO, meaning we're sending less bytes to the storage device for a given operations, for writes or for reads. Now, when we do other operations, like for example, checkpoint or backup, we're sending a lot of data down to a storage device because we're trying to minimize the round trips against the storage device. However, when it comes to transaction log, you will notice shortly on the next slide, IO tends to be on the smaller size of the scale, and that's important because storage devices all behave differently based on IO block sizes. They just do. Right? They don't provide the same latency consistently for every single IO block size. So that's important to understand because storage subsystems actually do have to be sized. Right? It's not like you just go pick from a menu and you know that storage device is just going to do great. It's going to handle everything you throw at it just fine, right? Storage devices do have to be sized, and that you have to understand whether they can fit your workload adequately. And so IO block size again is the number in bytes of the actual read request or write request that your application is issuing. In this case, SQL Server. IOPS is simply how many IOs per second. So how many operations are taking place in a given second. And so IOPS, if you put two and two together, what I said before, IOPS can actually have an associated block size with it. Right? It's not the same to say IOPS at 4K IO block size or IOPS at 1 megabyte IO block size. Those are completely different measurements. So in that sense, I think of IOPS like currency. People say, oh, I can do 400,000 IOPS. At what block size should be the question that you ask, because that's not super impressive if you're measuring every IO at 1 byte. Right, or 512 bytes being realistic. If you tell me that you can do 1 million IOPS at 1 megabyte, that's more impressive. So those kinds of things are important to discuss and take into consideration because your application is going to generate a number of IOs per second, and you're going to have an average IO block size. But it doesn't mean that every single IO is going to be handled at a good latency, because you may have outliers that are going to generate a lot of latency because they're larger or because they're smaller and your storage subsystem can handle them very well. Anyway, it gets complicated from there. but that's largely the idea behind IOPS. So you get an idea, not a true measurement of how fast your storage device goes. This is another measurement of performance, right? So like latency is one of them, obviously, IOPS is another one, and throughput, which is simply the number of IOs that have taken place and the aggregate of all the request sizes during a given second, right? That's throughput. It's typically measured in gigabytes per second these days, right? If your storage device does megabytes per second these days, right? This is the year 2021. You should throw that storage device away, right? You should be generating multiple gigabytes per second of throughput because this is how things go today, right? We're talking orders of magnitude different than it used to be back in 1998 when I first touched my first storage device, serious enterprise storage device. Anyway, let's look at this graphically, right? So let's think of then, thanks to Jimmy May and Thomas Kaiser, former SQL cat, for this slide. It's been handed over through several generations, so I still continue to use it to this day. This is your storage device. Okay, simply put, just simplified. That's where the IOs are going to land, and we're going to be reading from. That is a timeline, right, of IOs, an incoming IOs, a queue of IOs on the top, and then a timeline t equals 0 and t equals 1 in seconds. And so what we can do is place some IOs, some transfers on that transfer queue there. You can see that all the IO block sizes are different, right? Well, the IO request sizes vary. So 64, 8 kilobyte, half a kilobyte, blah, blah, blah. Now, the concepts that I mentioned in the slide before go like this. The average disk seconds per transfer, right? That's the latency. So how long does that a given IO take to complete? So if I send one IO over the timeline, right, through the queue, and how many IOPS would, I'm sorry, going back here. The latency will be, if I take a single IO, it goes from, my host, which sits on my left-hand side here, to my storage device. That measurement of how long that IO took to complete, that's my latency, right? It's typically not a full second. It's typically just a fraction of a second. As a matter of fact, most latency today should be measured in microseconds. That's another point of discussion here, right? Storage devices these days are much faster than milliseconds, right? Where we used to talk about, transaction log being able to handle IO between 5 and 10 milliseconds. It's 2021. You should be talking microseconds, which is thousands of milliseconds, right? Anyway, IOPS is, simply put, again, how many transfers we performed in that particular second. So we have here 6 IOs, right? So that's effectively we have 6 IOPS for this particular example. I know that's kind of silly, but this is a very simplified a graphic here, so you guys can understand the concepts here. And so throughput, right, or bandwidth is how many bytes have we transferred during that second. In this case, we do the math of how much data we transfer here. We have 152 kilobytes. Or I believe that's the math anyway. And so the other concept is what is the average of disk bytes per transfer, right? Or my average IO block size, or my average IO request size. In this case, I can add, over a given amount of time, I calculate, I divide all the IO requests, I add up all the request sizes, and I divide by the number of transfers, and then I get the average IO block size, and that's another interesting number to keep in mind. And so the other number that's important is, the other metric that's very important is, what's the queue length, right? And queue length simply specifies, is my device catching up with me, right? That doesn't mean that queuing is a bad thing, because sometimes you're not sending enough work, right? If you have a queue that stays low because you're not generating a lot of IO, that's totally fine. But if you have a queue that's always full, and your application is constantly seeing high latency, and it's more of a transactional kind of operation where you're expecting those IOs to complete faster, well, having a long queue of IOs waiting to be completed, that's a bad thing. But if you're having a more bandwidth intensive operation, where sending a lot of IOs down to your storage device and queuing them is totally fine and totally expected, and you're getting good bandwidth, good throughput out of your storage system, that's a good thing. So queuing isn't necessarily a bad thing, but queuing also isn't necessarily a good thing. You need to understand what situation you're in and whether what you're seeing is a good thing or not. Anyway, not going to get into super detailed scenarios here for queuing, because queuing is literally something that can take us, oh God, hours, probably days to discuss, because there's a whole theory around queuing and math and graphs and things that I don't understand myself. So let's not get into that today. Anyway, let's get into SQL Server IO Basics, because this is super important for all of us to understand, or at least kind of revisit. If you guys are probably familiar with all of this. Number one thing that I believe is super important to understand is that SQL Server follows the write-ahead logging protocol. And what that means is that SQL Server will always write things to the transaction log before it does anything else. Okay, and the reason for that is that SQL Server is a relational database management system, and as such, it implements the ACID characteristics of an RDBMS. And ACID stands for atomicity, durability, atomicity, consistency, integrity, and durability. And the durability part of SQL Server is enforced by the write-ahead logging protocol. Okay, and there are only two situations on which SQL Server will move forward without ensuring that the things were written to the transaction log. And very simply put, those two things are: number one, when you have an in-memory OLTP table, when you use Hackathon, right, the feature formula, code name Hackathon, and you're writing, you have a table that is a volatile table, right? You're not persisting that table. You're keeping it completely in memory. Then we don't have to write anything for that table, right? So the engine ignores. Just doesn't. The engine does not worry about IO generated for that particular table, because it's all kept in memory. That doesn't have to be persisted down to a storage device. And the other feature of SQL Server, where it doesn't have to wait for transaction log writes to move forward, is delayed durability, right? You can actually specify some tables to have the delayed durability feature. And what that means is that SQL Server is going to not necessarily wait for that transaction log write to be completed for the transaction log records that comprise your operation. Rather than doing that, it's going to queue them. It's going to keep them pending and issuing them whenever, right? It follows an algorithm for flushing them, so you will continue to get some durability of your data. But if your system crashes and it hasn't persisted some of the things that you have setting in memory for that table, those transaction log records that haven't been flushed for that table for which you specified delayed durability, you will lose data. That's just how it is, right? And so for durability, again, write-ahead logging has to be followed. So everything has to be written to the transaction log for SQL Server for data durability to persist. And so how does SQL Server write to the data files though, right? We talked about write-ahead logging, which is writing transaction log records to the transaction log. Well, for the data files, you have a series of mechanisms for writing data to the data files directly. But there are two that you have some knobs about to control, and the main one is checkpoint, right? So SQL Server writes to a transaction log, but it doesn't flush the data files right away. As it performs transactions, as it commits those updates, deletes, inserts, and so forth and so on, any modifications to database pages or data file pages that are sitting in the buffer pool are just listed in memory as dirty buffers. And so those dirty buffers at some point have to be flushed down to disk, right? In order for you to have memory available for other operations. And this is it's done through a process called checkpoint, right? It takes a series of different dirty buffers and it flushes them down to the corresponding data pages. And so checkpoint can be a throughput intensive, right? Just like write-ahead logging is more of a transactional thing. Checkpoint is very much a throughput intensive operation. When your system is running low on memory, lazy writer will kick in. And lazy writer is just a forced checkpoint, right? What it goes and sees, my system needs memory. Let me go ahead and issue a thread that would actually go around my buffer pool and figure out which dirty buffers should be flushed because they have been sitting there for way too long. And now I need that memory to perform other operations. That's kind of how it goes. And so you also have bulk operations, right, in which the database engine will accept IOs directly against the data files. It will perform some write-ahead logging for those, though, because when SQL Server performs bulk operations, like, let's do a bulk insert, for example. When SQL Server does a bulk insert, it'll actually write on your transaction log which extents are being modified by that bulk operation. So if you have a failure of your system, a crash of your system during the middle of that operation, you know exactly how to roll it back because you know exactly which extents were affected by that bulk operation. Okay, and so that's actually very important. And there's something called there's a bulk change map within your data files that indicate which parts of your data files have been modified by bulk operations as well. And so that's another way for SQL Server to write data directly into your data files. And there's also eager writes triggered against your data files. So as you perform those bulk operations, depending on the version of SQL Server, there are some considerations there of how that actually works. Those writes will also generate IO in a different pattern, as you perform those bulk operations. Now, super important to understand is that SQL Server mainly relies on asynchronous IO for the operations that it has to perform. So if you are actually considering, how does SQL Server perform all of these IO? Is it actually just, is there a thread within the SQL Server process that's just sitting there waiting for an IO to complete for any of the operations that we just talked about? The answer is no, right? The SQL Server always tries to issue asynchronous IO. So a worker thread may issue an IO, right, for a specific task, and it may not be that same worker thread that actually receives the signal saying that IO actually completed, right? SQL Server just moves on because CPUs and memory move way too fast, comparatively speaking, versus storage devices. It doesn't make sense for the engine just to sit there waiting for IO to complete. And so 99.999% of the time, the engine doesn't wait for IO to complete, right? It's just that IO, and it just sits there and waits for that. Eventually some thread will pick up that completion of that IO. But in the meantime, the engine is going to move on. Now, what may happen is that IO took way too long. The engine noticed that IO took way too long, and it will tell you that IO took way too long. So that's the case, for example, when you see on your transaction log, on your error log, you see that dreaded error that says that you have a number of IOs that exceeded 15 seconds to complete. And that's why, right? So the engine just sat there waiting for IOs to complete, and then some of them actually took longer than 15 seconds to complete. By the way, that doesn't mean that you didn't have any IOs taking less than 15 seconds to complete, right? You had plenty of those too. It's just that 15 seconds is kind of that threshold when the engine is saying, dear Lord, what are you doing? This is bad. That's kind of how you should think about it. When you get to that point, when you see those messages, things are awful, right? And so, but that's kind of why it happens, right? The engine, it's not like everything came to a screeching halt. Things were happening. It's just they weren't happening fast enough because the engine was just waiting for those asynchronous IOs to complete, and they took over 15 seconds. And that when you see those messages in the error log, that's kind of what it means. Now, if you kind of try to put the two concepts together here and with some some context around what the engine does. And SQL Server performs all these different operations. And you can see here in this table all the different IO block sizes that that SQL Server issues for the different operations that it performs. Now, transaction log writes don't have to be 512 bytes, right? That could be larger than that actually. If you're working with 4K drives, drives whose sector size is 4K, every single IO is going to be 4K, and so that's important because if you have drives that are different, then you're going to experience some issues. Where you have some drives that are 512 byte sectors versus drives that are 4K sectors, you may experience some issues. There's plenty of information out there on that. But transaction log writes can also be bundled, right, or kind of grouped together. And so SQL Server has some mechanisms for doing that. And so when it does that, SQL Server could issue up to 60 kilobytes worth of transaction log writes at the same time. And so that's to be efficient and not wait for IO for every single little thing that it has to write. Sometimes it makes sense to bundle things together a little bit and then flush them down. That doesn't mean that it's not doing write-ahead logging, right? It's just kind of caching IOs as fast as it possibly can so they can flush them in a more efficient way against the storage device and still provide that availability and durability for the system. Now, checkpoint and lazy writer, you have there a variability of IO block size as well, so between 8 kilobytes and 1 megabyte for those IO requests. And so when you checkpoint a very busy system, you will see potentially multi-gigabyte per second IO as you flush all of those dirty buffers down to your storage device. Read-ahead scans, for example, if you're scanning an index, you will trigger this mechanism. Depending on the version of SQL Server, you could see IO requests from 128 to 512 kilobytes, and so forth and so on. Backup and restore is another one. Funny enough, backup and restore is pretty much one of the only ones, one of the only operations whose IO size you can control. Right, there is a max buffer size. I'm sorry, max transfer size parameter for backup and restore that you can use for kind of tuning the IO request size, and that can help if your devices are overwhelmed from all the backups that you're sending, for example. Reducing the IO block size may actually help. Or if you want to, if your devices are not that busy and they can handle larger IO requests, 4 megabytes. It's a maximum max transfer size, you may issue those in order for you to achieve larger throughput and get better performance against your storage subsystem. So those are some interesting tidbits there about backup and restore tuning. Column store, file initialization. Column store read ahead and file initialization have some of the largest IO block sizes that SQL Server requests, right? 8 megabytes in size there. Anyway, you get the idea here. SQL Server never ever uses a fixed IO block size for anything, right? So when somebody says, "Oh, SQL Server has an IO block size of 64 kilobytes," you should say, "No, it doesn't," right? You should say you're confusing the recommended NTFS allocation unit size with what SQL Server uses for an IO request size. It's not the same thing, right? It's actually a myth that SQL Server uses 64 kilobytes IO for IO request. It's simply not true. Anyway, let's talk about database files, transaction log files, and file systems because this is kind of important. Number one thing is there are several kinds of file systems. I am a fan of NTFS, and that's been around, since the early days of Windows NT. Most trusted file system. It still works very, very, very well with SQL Server. There are some issues. There have been some issues over the many years, and SQL Server has been running on top of NTFS for the longest time. And performs well. Some issues, not a big deal. There's also RDFS, which is a sort of newer-ish. It's been around for a good while now. File system. It's also supported for SQL Server. And so some of the things for NTFS were addressed by RDFS, but RDFS doesn't have the same adoption as the NTFS does. And to be honest with you guys, if anyone asked me, should I use NTFS versus RDFS, I would probably tell you to go NTFS because it's tried and true. RDFS is is reliable these days. At the beginning, there were some bumps in the road there for RDFS, and Microsoft acknowledged and fixed. But your likelihood of running on an issue with an TFS, I would say these days is still lower than your chances of running under an issue with RDFS. But that said, that's more of a personal opinion. Microsoft will tell you that it's totally fine to run SQL Server on top of RDFS. You can also use a network attached device as the storage for your SQL Server data files, your transaction logs, and either your file table or file stream data. Right? In SMB, server message block, is also formerly known as CIFS, right? It's a protocol for accessing those network attached devices and placing your database files in there. So that's another way of keeping your SQL Server data. NTFS and RDFS are used for block devices, meaning those devices on which you ask for a given offset within a given LUN number within a given storage device ID, right? With SMB, you specify a UNC path and you say this particular server name and this particular share name and this particular path to a database to a particular file. I want the offset blah 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 within that particular UNC path. That's kind of how IO goes. The difference between those two, right? I don't see a lot of SMB being used out there for SQL Server. I would say it's mainly used these days for live recovery on backup devices, right? So you have some backup appliance that allows you to live mount your database in a way from your backup appliance. They mount your database. They typically mount your databases as through SMB shares that they offer. On SQL Server on Linux, let's remember SQL Server also runs on Linux-based containers. You have a choice of different ways of safeguarding the data for your database files, your transaction log files. In Linux specifically, you have two different file systems that are supported, ext4 and XFS. If you ask me, Argenis, what should I use for Linux? My answer is going to be XFS every time. ext4 to me is mainly dead. Can you use it still? Yes. Will it perform well? Yes. Is it the one where all the investments are going in terms of development and performance improvements? No, that is XFS. So my suggestion is stick to XFS for all things Linux. And when you need a network share to place your SQL Server data on for whatever reason, one reason will be shared storage for a backup. For example, I want to back up SQL Server to an NFS share on Linux. I'm sorry, to a network share on Linux. I would suggest NFS. That's actually the only supported network file protocol for SQL Server on Linux. And more specifically, you need NFS version 4.2 for things to work correctly. And so those are the file systems and the protocols that are supported by SQL Server between SQL Server on Windows and SQL Server on Linux. Now, this is complex, right? All of these things that I have mentioned, that they get even more complex when you put them all together in terms of, what does SQL Server do for even a single IO within Windows itself. And that's, remember, SQL Server on Linux is actually SQL Server compiled for Windows, run on top of SQL PAL. So some of the things that are mentioned here are not necessarily followed, but you're still following Linux's storage stack. And let's be clear. I don't expect you guys to read every single thing that I wrote, that I have in this slide, right? Because it's a tiny font. I mainly want to illustrate a point. Every single storage stack is complex because there are many moving parts. Every single storage stack has been designed to handle a lot of different situations. So they're designed generically, so they can work with a lot of very different things. And SQL Server is just one use case for them, right? So this is the storage stack for Windows, as it was not too long ago. Because if you actually squint your eye there and you look at the disk transfer times a rule of thumb there. The excellent SCSI reads are less than 9 milliseconds. That's insane these days, right? 9 milliseconds is just horribly slow in the year 2021. So I just wanted to illustrate the fact that storage stacks are super complex, and SQL Server IO has to go through some of these parts at least. And so that actually can cause problems. Understanding all of these moving parts can be difficult. And the one thing, for example, you can kind of picture in your head is how does anti-malware or antivirus work with SQL Server? Or first of all, hopefully you are not using anti-malware or antivirus with SQL Server data files. You are excluding your data files, but they basically work as upper filter drivers here on the, if you squint your eye there on the third box from the top down, that's where the antivirus would kind of live in. They will basically sit in there and wait for every IO request to come in and see whether it's sent to something that it's actually supposed to scan, then crack open every request if it is supposed to look at it, and then run it through its algorithm to detect whether it's a good IO or a bad IO for whatever definition they have. And so that is free latency right there, right? Because it's software injecting itself into the path of an IO and on its way to the storage device, and that can cause some serious latency issues. I have seen some of the most horrible problems for performance that I have seen in my professional career are related to anti-malware misconfigured for SQL Server. Anyway, when you think about hypervisors, right? We talked about the concepts of storage, and we talked about the file systems and all of that. You have to remember that you're running all of these things within the context of a hypervisor. And that means that you have some physical hardware that's actually being shared across many virtual machines. And even if you're running containers, you're likely going to be running containers on top of hypervisors. And the reason for that is that you want to establish security boundaries between those containers. Because if the workloads are not trusted between each other, then containers can start snooping on each other's data due to the way that CPUs work still today. So even if you're running containers, you're likely going to be running containers on top of hypervisors. And VMware happens to be the most common hypervisor used out there for SQL Server. And this is a kind of a high-level VMware stack. So you have the physical hardware there at the bottom, the VM kernel there, which actually is the privileged portion of the hypervisor that performs all the CPU scheduling and memory allocation, and it implements the access from your virtual devices into your physical devices and the resource sharing, right, part of the hypervisor. And then at the very top, you have the VM guest, which is your actual kind of packaged operating system guest with your applications and your virtual hardware attached to that. And so one important thing here, that one optimization that VMware did for the stack is the implementation of the virtual SCSI driver, right, which makes IO or requests go a lot faster from your VM into your VM kernel into your storage device. So if you're not using PV SCSI controllers on your VMs today, you should use it. It's free performance, excuse me, that you gain from leverage that. So suggestion is that you talk to your VM admin if you're using VMware in your infrastructure and implement PV SCSI adapters for SQL Server. That's definitely going to give you a big edge there. But you guys are getting the gist of this, right? You have some devices there at the bottom there, and you have all this stuff in between your actual application, your SQL Server, that runs on a virtual CPU running on top of this VM. Right? Troubleshooting all of these things doesn't get any easier the more layers you add to that cake. That's for sure. So the common hypervisors, VMware being number one by far out there. We at Pure see something like 90+% of the market running on top of VMware. And Hyper-V is obviously available for SQL Server as well, being a Microsoft product, has been around for decades now. But we don't see a lot of adoption for it on premises. Now, there's a modified version of Hyper-V that runs on Azure, so If you run on Azure, you are running on Hyper-V. It's just a very heavily modified version of it. There's also Nutanix AHV, Nutanix being a hyper-converged software solution. And we'll talk about hyper-converged in just a little bit, but that's another hypervisor that's supported for SQL Server. Red Hat also has a hypervisor where you can run SQL Server on top of, for Linux and other environments. And you can even run Windows guests on top of Red Hat's hypervisor, right? That's actually supported. And there are other hypervisors outside of these mainstream hypervisors on top of which you can still run SQL Server. So get the idea of this being that you understand that you can run SQL Server on a very different variety of systems, and that each and every single one has its challenges in terms of performance and understanding, what moving parts should you care for reliability and performance of your systems and availability of your systems as well. Anyway, continuing on with the discussion about protocols. I mentioned briefly some network access protocols, and those are important to understand. Well, when we're talking low level storage, we typically talk about the protocol of the SCSI protocol. It's been around for, oh my God, what is it, 80 years now? I'm sorry, 40 years now. SCSI has been around for a really, really, really long time. And so the SCSI is basically a way for you to send commands to a storage device, right? Where you can say, hey, are you busy? Hey, can you give me this data that sits on this particular offset for this particular log? Can you rewind the tape? Things like that were even embedded on the SCSI device because it will be used even for tape, but it still today can be used for tape. So it's been around for forever, and it's the preferred access for storage devices for the majority of what you see out there, right? Because it's just everywhere. SATA is basically a way of accessing a storage device in a serial fashion, and probably shouldn't be used anymore, right? Because if you're talking about SATA drive these days, it's extremely slow. Fibre Channel is a protocol for accessing storage devices over a network, and this is where it becomes a little bit more interesting, right? When you have the capability of accessing those block devices that I mentioned, whether you can format via NTFS or RDFS or ext4 or XFS on Linux over a network, right? Where you can rely on some additional functionality from your storage devices for a myriad of different reasons. So Fibre Channel is one such protocol that would allow you to send SCSI commands across a network to a storage device. iSCSI is another such protocol that would allow you to send SCSI commands to a storage device across a network. It also has been around for a really long time, and it basically encapsulates SCSI packets and makes them routable over a network. So you can, target devices that may be sitting on a different cage in your data center, or maybe even across the globe, right? Obviously, latency concerns notwithstanding there. But all of these things are basically going away now that we have NVMe. NVMe stands for non-volatile memory express. And NVMe, really, the way that I think about it is a replacement for SCSI. Right? So SCSI, being around for so long, was designed for a different era. It was designed for storage devices that couldn't handle tons of parallelism, and assuming that you would always have a lot of latency for every single IO that you placed. So the protocol itself is chatty and not very efficient and not able to handle a lot of parallel operations. That all goes away with NVMe, right? NVMe is designed for the next 40 years of storage devices out there. So you are already seeing a shift away from SCSI devices. Like even your laptops today, they don't come with SATA drives anymore, right? They come with NVMe devices, all of them, and even your SSDs today are not being accessed. The newer SSDs are not being accessed using SATA or iSCSI anymore, or SCSI anymore. They're all being accessed using NVMe because the protocol is so much more efficient, and Windows does support that, same as Linux. Now, another analog of Fibre Channel and iSCSI for the NVMe world is NVMe over Fabric. And I know it's a lot of different things to kind of take in, but the idea is you have a protocol to send I/O requests down, and another protocol to route those commands from that other protocol across a network. And so the analog to iSCSI for SCSI will be NVMe over Fabric for NVMe, right? And so that's a way that I think about it. Right? NVMe over Fabric makes NVMe commands routable over a network, so now you can access devices from your hosts that are sitting outside of it and perform I/O against those devices, enjoying the goodness of the NVMe protocol. So the devices, the list is long. I'm going to mention a few things in here. The one that you have here at the upper left is a persistent memory device from Intel, right? So it's called the Optane DC persistent memory. And so what that device does is basically sits on your memory banks for your computer, and then every single thing that you write against those persistent memory devices are safeguarded from a system failure, because the medium that they have is different than your regular DRAM or traditional memory that sits on your servers, which is volatile. Right? Whatever you write to a persistent memory device can actually be recovered after a system crash, right? And even several weeks, or I don't even remember what the time is, but it doesn't need to be powered to keep the data safeguarded within it. And that's important, because if it's it can be on the memory bus speeds, right, nanoseconds of latency, you can issue I/O extremely fast against this. Now, the thing is that if it's a memory device and you want to access it as fast as possible, you don't want to go through the storage stack of the operating system, because that adds latency to every I/O, right? And so it gets complicated, because how do you provide high availability for persistent memory solutions if you don't rate them? For example, you don't group them together, so perform mirroring of persistent memory devices and that kind of thing. So this is technology that you're going to see evolving and changing in the near future. There's starting to be a little bit of adoption for it. Microsoft is seeing adoption for it, definitely. And so the other way of safeguarding data within your servers as well is that what you see on the upper right hand there, on the upper right hand side, it's an Intel Optane SSD PCIe attached card, and that is also a persistent storage device, right? So that sits on your PCI bus. Whereas in your PC you will place a graphics card, and that PCIe slots on your servers, you would use those slots for things like this. You would place some very fast storage devices there, hopefully using some of the fastest medium available today. Optane being faster than NAND flash used in SSDs. So that can give you, low microseconds of latency for your workloads. And so that's another way of safeguarding data within your boxes. But you still have to replicate data or rate data in order for you to have high availability and have some data protection in case something happens to one of the cards. You must have another copy of data somewhere, and so hopefully you're replicating across to another box. And so typically what people do when you're using in this kind of storage devices is that you're using something like availability groups to replicate data to another storage device. And so the other ways of safeguarding data are SANs, right? Storage area networks and storage arrays. And at the bottom there, you see the ones that my employer makes. On the bottom left, you see flash array, which is our block device. And the list is long for options out there. there are great solutions from NetApp, Dell EMC, and a lot of others for block devices, right? And those the data that you put in those devices can be accessed via Fibre Channel, iSCSI, or NVMe over Fabric. And so you have a variety of ways to segregating data there. There's typically a lot of redundancy baked into these devices, so that you don't have to worry about RAID or data duplication or what happens if kind of scenarios. And the devices typically support some sort of replication at the storage level through various means. And you may want to rely on those as opposed to using availability groups, as opposed to using replication. Like sometimes it's just easier to defer the replication of data to a storage layer. And so we're actually going to have a little bit of a discussion there. It's just that we're running very low on time here. On the bottom right, that's a network attached device, right? That's a FlashBlade from my employer, Pure Storage. And so FlashBlade speaks some of the protocols that we mentioned before, NFS and SMB, where you can use for things like your SQL Server backups and your analytics for RDFS, or for your big data clusters and your Spark workloads and other interesting scenarios there. So understand that the list of devices that are available out there is extremely long. For network attached devices, you also have great solutions from Dell EMC, NetApp, or even Hitachi. So there's a very long list of devices available out there. Just understand that all of these other things that I mentioned before are kind of applied to some of these devices, and you certainly can use a mix and match of these devices for your enterprise out there. Anyway, finally, I think I wanted to close with a little bit of a discussion on block replication versus logical replication, because I think it's important to discuss. If you start thinking of all the replication technologies SQL Server has, you have your transactional replication, or your overall overarching replication concept within SQL Server, which is basically take whatever's been written to the transaction log, transform it into some commands, and replicate those commands to subscribers out there. There's also log shipping, right, which is more of a whatever you wrote to a transaction log backup, let me ship that off and then just restore it on the other side. Very simplistic way, very simple, very effective way of sending data around. There's always availability groups, right, which we mentioned. And availability groups are replicating log buffers, right? So you take a log buffer on one replica, on your primary replica, and make sure that log buffer gets hardened, whether synchronously or asynchronously, on other replicas. So what you need to think about is, well, I mean, when you use some of these technologies, you are cracking open data and you're sending data across to some other place. Sometimes it makes sense to just replicate things at the storage level and say, you know what, I have my data files, my transaction log files, and my storage device, just replicate those in some way, through snapshots maybe, or through some journal replication that's asynchronous, or maybe even synchronously replicating data from one storage device to another, right? These are vendors have tons of solutions out there, and sometimes it makes a lot of sense to just let your storage device or defer to your storage layer and handle those operations for you, because it tends to be easier on management and easier to scale. And where availability groups will have certainly struggles keeping up with workloads that are riding very heavily against them. You can see that naturally when you issue a reindex against a large table on AG. You wouldn't see that on a storage replications, block replication based architecture, because whatever's been written doesn't have to be cracked open and don't send a bunch of commands down, right? You're just seeing modifications on disk sent across, and that's it. So much more bandwidth effective from that point of view. Anyway, we run out of time, and I definitely wanted to keep the conversation going. So I have a lot of other presentations that I've been developing for the SQL community out there on group by and 8KB and so forth that you may want to take a look at, right? Where I go more in depth into some of the things that we discussed here today. There's my email address there. That's my LinkedIn, my Twitter as well. Warning, my Twitter is not safe for work at times, but I talk a lot of things about SQL Server. And if you keep an eye on the SQL help hashtag, we're definitely having good conversations in there all the time. Anyway, so I wanted to thank the DBA Fundamentals VC team for having me today. This time is always valued. So I am gonna let you guys go. And thanks for coming to my session today. I appreciate it.
Oh, thank you, Argenis. We do have one question that was pushed out that I did not get a chance to break into your session during. Does the NTFS formatted cluster size of a volume affect the size of a transaction log write?
That is a wonderful, just wonderful question, because it doesn't, right? The myth says that it does. Where if you have an NTFS allocation unit size of 64K, the recommended allocation unit size for an NTFS formatted file system, that doesn't drive SQL Server's IO, right? The fact that you have an AU, the NAU is just simply a boundary. It's kind of like an extent, right? There's actually no physical delineation for extent. It's just grouping these sectors together. In that same sense, an allocation unit is just whereas an extent is just logically grouping pages. An allocation unit on your file system is just grouping logically disk sectors. It doesn't do any much more than that. It's a divide and conquer metadata thing. So the file system can address things individually and keep track of things individually, but it doesn't drive IO. And when you issue an IO for transaction log or even for your data files, the AU on your file system makes zero difference, right? What it will make a difference is when you're allocating things, and hopefully allocating things is not something that you do frequently, because you should stay on top of your data file sizes and your transaction log file sizes, right? AUs start to kick in when you have to grow your data file, when you have to grow your transaction log. But even today, those operations have been made extremely efficient. So you wouldn't see much of a difference with today's storage subsystems. It wouldn't make much of a difference to have a different AU size. But I always suggest that people use the larger allocation unit sizes. That's not because it's going to help with IO. It's just going to help with less metadata for the file system, because your databases are getting larger, and that's a fundamental problem out there. It's a great question. Any others?
That was it.
All right.
So thank you very much to both Argenis and everyone who got to actually watch this presentation. Through the chat we've had during this presentation, I've seen several people talk about how wonderful this presentation has been. They've learned lots of new insights, new things to think about as they're going into setting up drives and hardware. So with that, we do thank you, Argenis.
Thanks for having me, you guys.
All right, so with that, we do thank you all for coming to our presentation, and we hope you will see you again soon. Thanks.